So the first example application of fork join pool is called applyAllIter. And you'll see why it's called applyAllIter in a second. It's going to apply some operation to every element in a list, and it's going to do this in an iterative way, using a fork join pool, of course. So what this is going to do is it's going to take the applyAllIter method is going to take a list, and it'll apply the operation, which is a function, to all the items in the list, and it's going to process these things in an iterative way, and you'll see what it means to be iterative in a second. Notice, just as a quick side note, that the parameters that are passed in here are treated as so-called effectively final. And what that means is that they are not going to change between the point where they're passed in as parameters and where they're actually used down here in the method. And so as a result, we can use them in the context of this anonymous inner class. This is something that was added in Java 8, and you can read more about it at that link. Okay, so let's take a look at this code. So what this is going to do is it's going to create a new recursive task, and the recursive task is going to have a compute method, because that's what you do. And this is defined as an anonymous inner class, right? An anonymous recursive task inner class. And then its compute method is going to do all the work in the function. We'll see what that does in a second. Notice again that because fork join pools APIs were designed before Java 8 existed, we can't use a lambda expression here. This would be so much cleaner if we could make this a lambda expression, but we can't because of the fact that this was designed pre-Java 8. So that's the computation that'll take place, and that computation is going to be invoked by the fork join pool passed in as a parameter. Remember, we made our own fork join pool, and that's going to be invoked in the context of that fork join pool. And invoke is a method, if you may recall from our earlier discussions about the different types of methods in fork join pool. Invoke is a method that will block the caller until the computation is done, and then it will return the result. So what we're going to get back here, as you can see, will be a list of items that have been transformed by applying the op to them, the op parameter to them. So remember, invoke is a two-way call. Here's, looking at compute. So keep in mind, this is this method here. So I'm just zooming in on compute now, just so you can see what it's doing. So compute is going to be used to implement the main fork join task. And what it's going to do is it's going to make, much like your program, much like you did for assignment 3A, it's going to make a list of fork join tasks. Now, in your program, I think you used your unsynchronized array. In this example, we used linked list, but same difference. So we're going to have a list of fork join tasks called forks. That should look familiar. And then we're also going to have a result list called res, which is also a new linked list. So this will hold the fork tasks. This will hold the results of doing the computations on the fork task. Okay, so far so good. What we're going to do now is we're going to iterate through the input list. So this is the list that was passed in here. This is a effectively final variable, so we can use it in the context of the anonymous inner class because it doesn't change anywhere. So we say for each element t in the list, we're going to make a new recursive task as yet another anonymous inner class. Again, boy, it sure would be nice to have lambda expressions here to clean all this up, but so much for that. We can't do that. So instead, we have to make an anonymous inner class. And the compute method in this anonymous inner class is going to take the op parameter, and it's going to apply the function on the element in the list. So for each element in the list, we're going to make a new recursive task whose compute method will apply the operation on that element and then return the result. So that's what's happening there. We're making a new recursive task. In your assignment 3A program, we had a helper class to make this a little cleaner. But it's the same idea. We're just using an anonymous inner class to fit it all in one slide. So we make a new recursive task that will apply the operation on the parameter and then return a result. And then we fork this thing What does that do? Remember, fork arranges to execute this in a thread in the pool, and it goes ahead and adds it to the forks array. That's, again, very much like your assignment. So by the time this loop is done, this thread will have forked everything and stuck it on its deck. So it'll have a deck that'll have every single item, or at least until we start getting stolen. It'll start pushing every item onto its deck. That thread will put it onto its deck. And the reason that this works is because the other threads in the pool are going to say, aha, this guy's got stuff at the end of his deck. So I'm going to go and steal the stuff off the deck when this thread is not, when this thread is busy doing other things. So that's work stealing. And then after all the stuff has been set in motion, the originating thread here is going to go ahead and iterate through the forks list. And for every fork join task in the forks list, it's going to go ahead and join with that task, which will give the result back, right? Because that's what join does. It gets the result. It waits for the task to be complete, and it gets the result back. And it adds that result to the result list. And then, of course, when we're done, we return the results list as the result of this particular function. So this particular approach is very simple to program and very easy to understand because it's all iterative. You just go through the original list, passes parameter, create a recursive task for each element, apply each operation to each element, return the result. All that stuff gets thrown into the fork join pool, and the other threads steal the results. And then we have a loop that waits for all the results to come back. We join everything up together into the results list and return it. So I think it's very simple to understand. Here's kind of what it looks like if you were to see it, sort of visualize it. So when this thing starts to run, the invoke method will put this first recursive task into the shared queue. Because keep in mind at this point, we're not inside the fork join pool yet. This is an example of a non-fork join task client. This guy is non-fork join task client. So it inserts the task into the internal shared queue. And then everything starts to run. So as we go through this list here, worker thread 1, let's say worker thread 1 will pull task 1 out of the shared queue, and it'll start doing this processing, and it'll throw all these subtasks into its work queue. And the highlighted code here is what's running in the original recursive tasks, the task 1, and the compute method of that thing. And so it'll throw all these things into into its work queue, into its deck, and then the other threads in the pool will come along and steal from that particular deck. And I think I actually, let's see, did I do that right? I might have got that backwards. I may have to fix that. Yeah, it'll actually steal from the end. It doesn't steal from the beginning. It steals from the end of this deck. So it'll steal from this part. So it'll be stealing, stealing, stealing. All the other threads start to run. So work stealing overhead is high because we have to steal everything. But copying and method call overhead is low. There's really no additional copying of anything going on here. And there's really very few extra methods. The copying and method call overhead won't make sense until you see the other implementations, which we'll talk about next time. And then for this part here, all the worker threads pitch in to compute the subtasks. So they're all helping to clear out the queue and finish all the processing, including the one that's calling join. That'll also pitch in as well. So everybody pitches in to help out. So that's the collaborative Jiffy Lube model of pitching in to do the processing. Okay, so that's the end of that discussion. This should look very much like your program that you did for assignment 3A.